Hello, welcome to another Stat 432 video. We have some starter code on the screen. I have my notes. Let's investigate binary classification in R. Right, so this is sort of a continuation of the previous video that was about logistic regression, except now that we have this notion of, sometimes we want to classify something that's binary, that is, it only has two possible outcomes. That doesn't mean we have to use logistic regression. We can, but we could also use k-nearest neighbors, trees, anything else you can think of. But how we evaluate those models might be slightly different. So that's what we're going to talk about here. Right. So to get started, we need sort of a few packages. So for one, we're going to use this UCI data package to load a data set. But this package is not on CRAN, so to install it, you'd have to use this command here. But if you don't have the DevTools package, you would have to first install that. I might note that the author of this package, if you check out that person's GitHub page, you might notice that they are also a University of Illinois affiliated person. So let me check that out. Okay, so that package for data. Tibble package to make data look like a tibble just for easier printing. Our part is because we might fit some trees. Our part plot to visualize those trees, although I might not actually do that. Caret to fit k-nearest neighbors models. Loading that whole package just for that one function is a little bit overkill, but we're doing it anyway. And then this CVMS package, which I honestly forget what it stands for, but we're going to use that. So a note there. Right now, we're sort of operating in a very simplistic world where we have this nice already wrangled data. We're predicting one of the columns using the other columns as features, and we're using these really simplistic methods, and we're doing really simplistic evaluation of our models. A little bit more detailed today, but in general, very simplistic evaluation of our models, and we haven't done resampling yet. That is, we haven't touched cross-validation. So what I'm saying is right now we're sort of really working on basics. When we get to more practical matters, we're going to introduce sort of systems or pipelines for doing machine learning inside of R. We might use Caret, we might use MLR3, we might look at the tidy models approach. We'll sort of mention these things, and basically, I think you're probably finding that there's a lot of repetitive tasks we're doing. For example, like test train splitting data. Like, there's got to be a faster way to do that, and there is, and we'll show that eventually. But so this CVMS package is going to be our sort of first foray into sort of working at a higher level of abstraction and letting someone who already coded something do jobs for us. But so keep that in mind. Even after I use it, I'm going to go back and do something sort of quote unquote by hand or from scratch in R, just to show that if you know the definitions and a little bit of R, you can get pretty far. But sometimes you can get a lot further faster if you know the right packages. Anyway, so let's get some data here. So the data we're going to use is, again, this data set here is from this package. I'm going to coerce it to be a tibble. I suppose I didn't need to do this since I loaded it, but oh well. And then I'm going to throw out any missing data. Should you do that in practice? Probably not. But we're working simple right now. We'll deal with that later. Okay. I'm also going to prepare the data a bit. So in particular, I'm going to sort of do a little wrangling to the response variable. It's not important at this moment that you know how to do that, but I'll show you the result of that. And I'm going to throw out a variable that's just an identification that we wouldn't want to use for prediction. Then I'm going to test train split the data. Then I'm going to estimation validation split the data. Let's do that real quick. Then I'm going to look at the data. But because I've zoomed in my RStudio so it's easier for you to see, less of it fits on the screen here. And for whatever reason, this data set, the way it was prepared, has very long column names. So it's sort of hard to see some things. So instead of the head command, I'm going to use the view command, which pulls up this here. So essentially what we have here, we could actually check out the documentation real quick. What is it? BCW original? Yeah, there we go. Okay, so what do we have here? Sorry, I need to move my camera. So this is a breast cancer data. It originates, I forget where the exact origination is, but this can be, oh, here's the source here, but it can be found on the UCI machine learning repository. So this is a very classic data set. Ultimately, some samples were collected, some information about those samples was recorded, basically about cancer cells, and someone looked at it under a microscope or something. I don't know medicine or biology. And then it was determined to be either benign, that is not cancer, or like a non-cancerous tumor, or malignant, that is, it's cancer. So originally it was 2 for benign and 4 for malignant. What you'll notice that I did was I changed the class variable to just say benign or malignant, because that'll be kind of easier to keep track of. But importantly, it's a factor variable with 2 levels, benign and malignant. And remember, the order of this matters for something like logistic regression, where for a logistic regression, the first level, benign here, would mathematically correspond to 0, and then the second level, malignant, would correspond to 1. The other thing that we're going to talk about, so if we consider, we're going to make some confusion matrices, right? And we want to talk about, false positive, true negative, et cetera, et cetera. So to do that, we have to define a positive class. And it's completely arbitrary, but depending on what we define as positive, that will influence all the later metrics that we calculate. So for the sake of this quote-unquote analysis, so this is really not much of an analysis, we're going to define malignant to be positive. So in this sort of like medical testing framework, positive generally means like you have the disease. So in this case, cancer is the disease, and malignant means it's positive. So everything we're doing right now is sort of very relevant. False positives and false negatives are very important to those of us at University of Illinois right now, because we are doing a lot of COVID testing. At the time of recording, we've done over 300,000 tests. So the false positive and false negative rates in those are pretty important given how many we're doing. But we're not here to talk about COVID. We're here to talk about, in this case, binary classification and breast cancer. Okay, so I'm just going to consult my notes real fast. All right, so we want to fit some models. And my goal here is not really to fit the best possible model. My goal here is to fit illustrative models. So I'm going to fit a k-nearest neighbors model, a tree model, and a logistic regression model. So first I'm going to fit a k-nearest neighbors model. So we use the knn3 function for classification. Class is the name of the response variable. And then just somewhat arbitrarily, I'm going to pick a couple predictors just so this thing doesn't work too well. So I think I'm going to do, I'm going to check my notes, clump thickness, whatever that means, and then mitoses. So this variable here. And I'm going to fit this to the estimation data. The data equals the estimation data. Okay, cool. That works. And I'm just going to use default parameters for everything. Right. Then I also want to fit a tree model, which we do with our part. And I believe, otherwise, the syntax is the same. And I'm going to align these equal signs. And then I'm also going to fit a logistic regression, which we use GLM. So a lot of this is the same, except I also need to say family equals binomial. Let's fit these. Cool. All right. Okay, what next? So now what I'm going to do is so again, back here to the levels here. So, excuse me. The response can be benign or malignant. And so we have anointed the malignant class as the quote-unquote positive class. So what I want to do is for each of these models, I want to store the predicted probabilities of only malignant on the validation data. So let's try that. So first let's do it for KNN. And so I want to do predict mod KNN, the validation data, which is BC val. Okay, so notice what this does is this gives me actually a data frame. But what I want is a vector for just this column here. So I'll do a little subsetting like that. Okay, so this is what I want. So I'll call this, excuse me, prob underscore KNN. Cool. I gotta remember to go back and run that. So I'm pretty sure with a tree, the syntax is roughly the same. So if I run just this part of it, yeah, this is looking about right. Yeah, there's 2 columns, one for benign, one for malignant. You know, these add to 1, so they are what we think they are. So if I do this, yeah, this is still a vector. It's just the observations are named. That's fine. So we'll call this prob tree. Okay, cool. Notice that I'm sort of breaking down my code as I do it. I'm running just this part, then doing the subsetting, then doing the storage, just to make sure. I probably could just write that line, but it's good to check that what you're doing is what you think you're doing. Let's see how that could bite us real fast. So let's say I tried to just slip GLM into here. Oh, that doesn't work now, does it? Okay, so let's get rid of this. Those aren't probabilities. You can't have a probability of negative 1.8. Oh, that's right. I need to do type equals response. And these are exactly the probabilities that each observation in the validation set is malignant. Because again, remember, logistic regression is solely focused on the positive, or not the positive class necessarily, but the class that's second in the response vector. Sorry, response factor. So that's what I want. We'll call that prob underscore GLM. Something like that. Okay, cool. What's next? Okay, so now I want to, actually I'm looking at my notes and I'm wondering if I want to do this a slightly different way. Let me check something real quick. Yeah, so what I'm gonna do is I'm not gonna store the results for just KNN. I'm gonna store the results for everything. What I'm actually gonna do is kind of repeat what I did there. But so what I'm going to do is I'm going to say, ooh, okay, I'm going off the book. I have notes, but I'm going off of it. This could get dangerous. But if I run into an error, that's good, because then we can fix it on the fly and we can see debugging. So I'm going to say results is going to be a tibble. And so I want 2 things in the results. So I want the actual values in the data set that I predicted on, that is validation, and then all of the probabilities stored together. So just so it doesn't yell at me. So first I will do actual equals BC val $ class. And then I'm actually just going to take this and throw it in here. And actually, just to be certain of something, I'm going to set a seed here. And then I'm going to do it again right here. Just so the results don't get unaligned, especially with respect to k nearest neighbors, just because if there happen to be a tie in distance, although that should be really rare here, and we're using an odd k value, but just in case. Okay, so I'm going to rerun that. And I could have just put this only in here, but I might reference these directly, and I'm being a little sloppy, but that's okay. So let's run this, and let's have a look at it. Okay, so now we kind of have a summary of what's going on here. So here are the true values in the validation data set. And then what we have here is for each of our 3 models, the predicted probability of the malignant class. We got to remember that. So here, each of the models is showing a low probability for malignant, and it actually happens to be benign. That's good. So now what I want to do is evaluate how well these things work. But right now I only have probabilities, so what I need to do is make classifications and then calculate certain metrics, right? So what we'd really like to do is create a confusion matrix like this, where 0 is benign, 1 is malignant, and then calculate all these metrics, or a bunch of other metrics too. Yeah, so basically we want to do all of this, and that's where we're going here. So what I'm going to do is use the evaluate function And this comes from this CVMS package. Okay, so I think we should first look at the documentation. Here. Okay, so it wants some data. It wants us to tell us which column is the true values. That's what it means to target. Prediction columns. So in this case, we're going to give it one column. So we're going to evaluate one method. So we're going to do k-nearest neighbors, but it's in that tibble already. So that's good. Type. What is type? Okay, so Gaussian if we're doing regression, binomial for binary classification, that's what we're doing, or multinomial if we're doing multiclass. We're doing binary, so we'll supply that multinomial. Don't need this, don't need this, don't need this. We need this. Okay, so remember, by default, when you do classification, you say, well, if the probability of, say, the positive class is greater than 0.5, classify that way, else classify the other way. But we can modify that cutoff. So it looks like this function is going to make classifications for us based on the probabilities that we put into it, but it'll allow us to modify the cutoff. That's cool. It also makes us specify the positive class. Also cool. So we're about to type a lot, but I think by doing it, it's going to be very clear what we're doing. And then we can specify metrics. It does a lot by default, but we're going to add one. And then it's going to spit out the prediction. Okay, this is cool potentially. All right, so let's try this. So just checking my notes. This package is new to me, so I could screw this up. Let's find out. So the data that the evaluate package is going to take is the results. Okay, can I get autocomplete here? Okay. It won't autocomplete on a new line. That's unfortunate. Let's try this real quick. Target columns is going to be, so the column we're going to target for KNN is this column. Oh no, sorry. The target is actual. Okay. Autocomplete, predicted columns. That is going to be this, because we're dealing with k-nearest neighbors right now. Okay, cool. I wish it would autocomplete without having to do a big line. We'll fix it later. Okay, type, we said, is going to be binomial. For binary, what comes next? We don't need that. We don't need that. We don't need that. We're going to specify this even though it has a default value. But we're going to make it 0.5. And we're going to specify the positive class to be malignant. And we're also going to say metrics. Wow. Okay, sorry. I don't need autocomplete anymore. So this by default does a bunch of different metrics, but if I can add one if I do something like this. And it has to be one that exists in the package, but this is the one that I want that for some reason isn't there by default, I think. Have I specified everything? Yeah. So I'm going to call this, well, let's just run it once. Okay, that did something. But I'm going to store it as knn_eval, and we'll do some stuff. Okay, let's view it. So knn_eval. So right away, we see some good stuff. We see a lot of good stuff. So we see the balanced accuracy, the F1 score, the sensitivity, the specificity, the positive predictive value, the negative predictive value, and a bunch of other stuff. But because it's returning a tibble, it doesn't show it unless it fits. So we could do view eval. View KNN eval to pull up the viewer here so we can scroll. We see a lot of good stuff here. So right off the bat, I mean, most everything here is there plus a bunch more. So that's great. But so, for example, you might say, oh, the accuracy is 0.909. Well, is it? Or is that just what's printing out by default here? So if we understand a little bit about what's happening here, if I return the accuracy column, it now returns a vector of length 1. We see that it's actually, there's a lot more digits there. So this is something that's printed out. This is the actual value minus some digit magic in the background the R is doing. Clearly, this is actually a repeating fraction, but that's okay. But so, like, if you're a student in 432 and doing Prairie Learn, this might not get you the answer this is. So it's important to know how to pull out specific values from a data frame like this or a tibble like this. what else can I say about this? So we can pull out other values, like for example, we could pull out the sensitivity. Cool. We could also look at KNN underscore eval. There's a ton of stuff in here. We could get the area under the curve. That's great. Oh gosh, there's all sorts of stuff here. How about predictions? Oh, I don't know why this is happening, but so this returns a modification of what we gave it, which is the target variable, the predicted probability that we put here. They've renamed our things a little bit, but oh, it returns the output of using a classifier on those predicted probabilities with a cutoff of 0.5. So we could very easily change that cutoff and change how all this works. Okay, what else is in here? KNN eval. I don't even know what all this is yet. Oh, there's a confusion matrix. Okay, I really wish it wouldn't do this. That's just like a... Okay, so this is a confusion matrix, except they're being very nice about it. So instead of displaying it as a matrix, which we'll do in a minute, they're saying, well, if your prediction is benign and the truth was benign, well, and positive is malignant, well, then that's a true negative. If the real was malignant and the prediction is malignant, that's a true positive. If the truth was benign and you label it malignant, that's a false positive. Hey, that's cool. But also it shows what it would be if the positive was benign. And then it shows how many falls in each cell. Let's see if we can't plot that. So one thing to note here, and this is maybe something I don't understand about this package, but there's probably a good reason for this. They're outputting a list with one element. So to truly get at that element, we need to access it like this. So now we actually have the confusion matrix. And it turns out, if we use the plot confusion matrix function from that package, CVMS, and then put that confusion matrix there, here we go. We get a really pretty plot, which is a confusion matrix. I think we might all agree that it's a little more feature-rich than this one here. So there's a lot going on here. So might be a little overwhelming at first, but let's break it down. So first of all, it says 21.8% of all the observations in the we're dealing with the this is a validation matrix basically. 21.8% were truly malignant and predicted malignant, and so on and so forth, which is 21 observations. So we had 21 true positives. We had 76 true negatives. So the target here was benign. We labeled it malignant. So this is a false positive, and this is a false negative. Right. So, but then there's all these other numbers, right? So what these are is, so this percentage and this percentage here, they correspond to, well, if we condition on the target being malignant, well then 72.7% fall into this square and 23.3 fall into this square. But if we look at this, well, hey, what does that mean? Well, that means that this is the sensitivity. And hey, why don't we look at the specificity? 98.7, 98.7. Hey, that's pretty cool. So this is a real nice plot. I think we like this a lot. So really quick, well, let me check my notes. Yeah, so first what I'm going to do is, yeah. Well, no, let's hang out here for a second. So I want to note what the sensitivity and specificity are right now. So here's our sensitivity, here's our specificity. So like, let's say we change this cutoff to be higher. What do we think is going to happen to these two things? Well, let's find out. Wait a second. Nothing changed, but that's very surprising. What if I go the other way? It could be that the cutoff between those two doesn't make a difference. Okay, well, that's real interesting. So the difference between a cutoff of 0.5 and 0.8 didn't seem to make a difference. But so now what I did is I made the threshold way lower, right? So many, many, many more things are being classified to positive. So we see that reflected in sensitivity going up, but specificity going down. So we also see that here. So as a result, we have many more false positives. So, but that was really easy to do because I just changed this one little number here. But now I'm going to bring it back. Oh, I didn't want to do that. Okay, so now I want to make a confusion matrix a little more manually. So, I mean, this is all well and good, and you can use this, and that's fine. I don't see why you wouldn't. But I just want to prove to myself that I can do this in a more manual fashion. Okay, so to do that, I'm going to use the table function. And I'm going to say the actual values are, where are they? This thing here. And the predicted values. So now I need actual classification. So we're considering a cutoff of 0.5. So I need to do, let's see, how did I do it here? Yeah, we'll just do it directly. So I do predict mod KNN on the validation data and type equals class. Let me just verify that does what I think it does. Okay, it does. Let's do that. Okay, so there is a very simple confusion matrix. Not as cool as this. And you might notice that the columns and rows are actually inverted a little bit. It says all the same information. You should never think that, oh, this upper left corner is the true positives. No, 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 no. You have to know what the positive is, and you have to know what a true positive is. Nicely, because we specify the positive class here and what the actuals are, it'll always take care of it for you if you do this. But you should know the definition of true positive, true negative, etc. I'm actually curious if I flip these. Well, no, that would put them in. Yeah, because so they're doing order of. So here they're doing ordered by factor level. Here they're doing order by positive then negative, but something to be aware of. Okay, so I'm going to call this conf mat. And then I think what I'd like to be able to do is just say, use this function on this thing. And I'm pretty sure this is going to work. And it says, that won't work. It says variable confusion matrix must be of type data frame, not table. Okay, so out of curiosity, what happens if I do tibble confusion matrix? That's not what I thought would happen. Oh, I need to do as tibble. Ah, okay. So this looks a lot like what we were looking at before when we extracted the confusion matrix from the CVMS results. So let's see what happens if I put this in here. Because it said it wanted a data frame, and a tibble is a data frame. Variable. Okay, so it's not quite there. It needs a little bit more information. So I'm actually going to say this is the data, I believe. And now let's do this. So, oh, no, it's confusion matrix is the first argument. Conf matrix. Okay. Okay, now the target column is this, so actual. And the next thing is predicted columns is predicted. And the count column is this n. Okay, and then I'm going to clean that up so I can actually see it. Run that. And hey, I get the same thing. Cool. Neato. Right on. Okay. Okay, so now what I want to do is change gears a little bit. So I fit this logistic regression up here. So let's say I didn't have this nice CVMS package or any of the many other things in R that would allow you to quickly get these statistics. I will note that I'm a big fan of the CVMS stuff because it makes it very clear, like, you have to specify the positive class. Sometimes if you rely on defaults, that can get really dangerous. Anyway, so what I want to do is I want to calculate the sensitivity, quote unquote, by hand or from scratch, using the logistic regression model. So probably the first thing I should do is get predictions from the logistic regression model. So how do I do that? Let's think. Predict mod GLM I want to do this on the validation data, so we're going to get like validation metrics here. BC underscore val, and I'm going to do type equals response just because that works better for me. Okay, cool. So if these are bigger than 0.5, predict to the positive class that is malignant, which is the second thing in the factor here, so that makes sense. Except I don't want trues and falses, so I'm going to do if else. So when that condition is true, we're going to return malignant, spelling is hard. And if not, we're going to return benign, spelling is hard. Okay. I said spelling is hard, but I think I spelled the hard things correctly, and I didn't autocomplete this. Okay, and then I want to make this a factor. Okay, and it has the same two levels as my original response variable, and they're in the right order. So this is cool. So I'm going to call this pred underscore GLM, and maybe I'll do this. Okay, cool. All right, so now I want to think about, what did I say I'm going to do? Sensitivity. Okay, so what is sensitivity? It's the true positives divided by the total number of positives. So what is a true positive? Well, that's when the actual is positive and the predicted is positive. So let's have a look. So let's look at when is the predicted, when are those malignant? I didn't store this. Cool. And then I want to look at BC val class equal malignant. I wish I could autocomplete. Okay, cool. So I want to see when those are both true and how many of those are there. So that's how many false positives, or sorry, true positives. And hey, look, it matches this number over here. Oh, that's funny. This is from a different model, but it is the same. We're going to verify that too. And then I need to divide this by how many are malignant. So we'll do some of this. Like that, and we'll do like that, and maybe we'll do like this, and then run it. Okay, so that is, for now, did I use the right models? So that's my sensitivity for now. I'm sort of making a note to myself. 7272. Okay, cool. So now I want to check this. If I get this wrong, this is going to be a waste of the last half hour. I'm going to have to do this video over again. I guess if you're hearing me say this, it all went okay. Time is a funny thing. Okay, so I want to check it with the CVMS route, but I don't want to rewrite all my code. So I'm going to do, I'm going to take this. So we'll call this now GLM eval. So remember, way back when, we stored all the results in a thing called results. So now, instead of supplying these probabilities, I'm going to supply these probabilities, right? Where were we? Here. I think everything else is good. So, moment of truth. Oh gosh. What do we say? Sensitivity? I did it. Okay. And like before, everything else is inside of there. I'm actually curious. Wait, let's real quick look at the confusion matrix to see if it changes at all. It'd be funny if these two methods were giving us almost the exact same thing. What do I need to do now? Hit tab. Just always hit tab, right? So I want the confusion matrix. I really wish, I don't know why that's happening. But anyway, this is good. So then we'll do plot, confusion matrix. I think these numbers are a little bit different. Okay, so that's a little bit different. Maybe let's see what happened if we crank up the cutoff to something really high with the logistic regression. I'm guessing that should get us more false negatives, I think. Let's see. Hey, I was right. Okay, cool. So yeah, this is how to calculate all these metrics from this video here. And again, the important thing is knowing what a true positive is, knowing what a false positive is, knowing what a false negative is, and knowing what a true negative is. If you understand what those are, you can sort of infer what all of the various metrics can tell you about. And ultimately, the definitions of these metrics you can always just look up. There's that awful Wikipedia page with just, a laundry list of them. I forget some of them myself. I think you should know what sensitivity and specificity are off the top of your head. Yeah. But yeah, so, and I think it's informative to go through this procedure here to sort of make sure you can calculate the metrics sort of from first principles. Or if you're comfortable with a package like this, that's also something you can do. I leave it to you which of these you would prefer to do. I think in some ways, this is better if you need to calculate multiple metrics. This might be better if you need to just calculate one metric, because here you have to specify all this stuff. Here you just need to make one prediction and then do one quick proportion calculation. So that's sort of up to you. So even though this video is about binary classification, I actually want to do a multi-class problem real fast just to introduce a little bit more of what Palmer penguins can do. Sorry, I've had these headphones on too long and they're pushing against my glasses and I need to... Anyway, so we're going to go back to the Palmer penguins data. And I'm going to remove the NAs. I'm going to test train split. We're just going to test train split. And let's have a look at the data. So remember that the goal here was to predict what species of penguin we were dealing with based on sort of where the measurement was taken and some physical characteristics of the penguin itself. Okay, so I'm going to use a tree model here. So I'm going to call this mod tree. I'm probably recycling variable names, which is not a great idea, but do as I say, not as I do. Not our part, Pat. So I'm going to do species. I'm going to use everything as a feature except for the year, just because. We're going to do data equals the training data. Okay, cool. You know what? While we're here, our part, our part dot plot this, just so we can. I think we've seen this before, but just to refresh your memory. Okay, so it really only ends up using a couple variables, or three: flipper length, bill length, and bill depth. Okay, cool. Okay, so I want to create a confusion matrix for this. So I'm going to do it the quote-unquote sort of manual way first. So I'll call it conf mat, and I'm going to make a table. Right, so the actual, so this, the actual here, so I'm going to do like test metrics now. So this $species, and then the predicted is going to be, if I do predict on this model, on this data, and I want to return the classifications. Let's make sure this is what I think it is. Okay, good. Create that. Have a look. Hey, okay, cool. So that's one way to look at this. The other way would be to steal a bit of our old code, which is up here. Put it here. And then I think all I need to do is nothing because I recycled a variable name. Sometimes it's useful. Hey, that's cool. So, like, this might be more useful, or this might be more useful. I don't know. It depends. Frankly, I don't know why they ordered these the way they did. I'm curious about something. Is it based on the order it sees them in? I don't actually know. Anyway, but so these percentages are still useful. So, like, if we restrict ourselves to the penguins that are truly chin strap, 0% of them were classified as Gen 2, 88.2% of them were classified to chin strap, and 11.8 were classified to Adelaide. So that's kind of like so even though it's a multi-class problem and we've defined sensitivity and specificity and those sorts of things for binary classification, you can sort of think of this as like an intra-class sensitivity, right? So, and we'll look at that in a second. Okay, so now I want to use my fancy package. So what I'm going to do is I'm going to make a tibble of results. So the tibble it's going to have the actual values being this. Is that what I want to call it? Yes. And then, because it's a multi-class problem, now I need to title the columns here very specifically. So in particular, I need to title them the names of the various species. Okay, don't yell at me at R. And so also what I'm going to look at real quick is predict mod tree on the, what is it, ping test data. Okay, cool. So notice if I did something like this, this would be the probability that each observation in the test set is predicted to be an Adelaide penguin, right? So we're going to put that here. And then we're going to do the same thing everywhere else here, except using the right kind of penguin. And then putting commas where they need to go. Okay, cool. So let's have a look. Okay, so that's good. So really, it's just a way of forcing this result here. I could have done this a lot faster, actually. I could have just added a column. This is not good code. I could have just added a column for these values here, but maybe I leave that as an exercise to the viewer. We'll call this penguin results. Okay, cool. So now I'm going to do the whole evaluate thing, except evaluate's going to be a little bit different because we're not doing binary anymore. So let's do evaluate. Okay. Oh, this time it will let me autocomplete. So the data we want to do is the penguin results. Oh, that doesn't keep going though. I don't know why it's like that. Okay. Target column is actual. Predicted calls. So now there are more than one. So there's actually 3, and I'm gonna go like this. So this is one of the predictor calls. This is one of the other prediction columns, and this is another one. Okay, I have to do this. So thinking now, what else? Looking at my notes. Okay, so we don't need, so we need to specify the type, right? So instead of binomial, this is now going to be multinomial for multiple class. There's no positive class anymore. There's no cutoff anymore because we're just using, whichever class has the highest probability attached to it is the one we classify to. That's kind of how we do multi-class classification. I am going to sneak in an extra metric. Why does it do the autocomplete sometimes or not? Anyway, I'm going to throw accuracy into this list, just in case it doesn't do it automatically. Does that work? Okay, cool. Don't look at that yet. I'm going to call this penguin eval. Okay, now if we look at these things, you might see some weird things. So like, what is the sensitivity? I'm pointing to my monitor. That doesn't help. What is the sensitivity in a multi-class problem? Interesting. So what I'm going to do is have a look at what's in here. And there's something new. This class level result. Ooh, that's interesting. Let's look. Okay. So now what there is within each of the classes, we have metrics. And so a sensitivity of 882 within the chin strap, that's exactly what we saw here. So you can sort of extrapolate your understanding of sensitivity, right? So in the binary case, it's of the things that are positive, what proportion of them are, of the things that are positive or 1, how many did we predict, what proportion did we predict to be 1? Well, now in a multi-class sense, it's, well, of the things that were chin strap, what proportion of them did we classify to be the chin strap? And here we see this 882, 882. But remember, oh gosh, this is going to be annoying. So this is returning a tibble, so I think I can do this, but it won't autocomplete. Let's do this. Let's do this. Temp. Is it not? Oh, that's tricky. I don't need to do that. I see. So for whatever reason, this is a list with one element. So first I need to actually extract. Then I can do this. and it's this one. Okay, that's tricky. I still like this package because ultimately I think stating things this way makes it very clear what you're doing. Anyway, while we're here, why don't we see the fancy way to do this, which is to just find where the confusion matrix was stored, extract it correctly, and then do plot. Oh gosh, I can't type anymore. It's been a long video. Same thing. Yeah, let's change one little thing. Let's do, I think there's a palette argument and I want it to be greenish. Hey, that's cool. Same numbers, just different colors. Okay. Checking my notes. Oh yeah. No, that's it. Okay, wow. So that was a lot. So to recap, if you understand the definition of true positive, true negative, and false negative, you can always just do manual calculations like this. It's basically just counting up things and calculating a proportion. If you're comfortable using this package, the CVMS, and this notion of sort of summarizing things like this in a results table and then calling the evaluate function with the correct arguments, go ahead and use that too. But at the end of the day, we have the definitions. We can count things up and we can calculate metrics. So for now, we're kind of just calculating metrics in a vacuum. When we get into the latter half of the class where we actually do analysis, it'll be really important what those metrics mean. So do be thinking about that. Yeah, but I think that's all I have to say on this. This video was way too long. So as always, if you made it to the end of the video, good job. And I'll see you in the next one.